gas station. There are n gas stations along a circular route where the amount of gas at the ith gas station is the value in the array. You have a car with an unlimited gas tank, and it costs the value in this other array of gas to travel from the ith station to the next one over. You begin the journey with an empty tank and at one of the gas stations. Given the two integer arrays, return the starting gas station index if you can travel all around the circuit once in the clockwise direction. Otherwise, return -1. If there exists a solution, it is guaranteed to be unique. Okay, let's look at the important parts of the input and see how that shapes our expected algorithm. You've got two arrays in C++. Those are vectors, but same. They are the same length. You can only travel forward, so this is clockwise, but really what that means is you can only go left to right. You cannot go right to left. So that simplifies things a bit. And return -1 if you cannot do the trip at all. And the solution is guaranteed to be unique. So there's only going to be one possible solution, if anything. So for any other possible starting point, you return -1. But if you find one good one, then that's when you return a value. Okay, so the order matters, and it's not necessarily sorted. So what that means is we're probably looking at a minimum runtime of linear. And if you don't know what that means, I'm not going to recover what big O notation is, but I'll put a link in the description below. But in general, a linear search is linear time, as opposed to binary search, which would be logarithmic time, which is significantly better than linear, but that is not possible because that relies on some kind of sorted property to be able to not look at every single element of the input array. Let's think about what a brute force solution is. If you were to step through each position of these arrays, so like position the first one, and then you run the simulation, you go through the entire loop. Okay, did it work? Yes. Return that. No. Continue on to the next starting point. And then you go to the next starting point, and you run the simulation again. So if you see the pattern here, you're going through the loop once, but for each step of the loop, you're going through the entire loop again. That's a squared property, so you end up with a quadratic runtime, O of n squared. That is significantly worse than O of n, and that would be the brute force solution. So we're probably not going to be able to come up with a worse solution if we tried. That said, generally speaking, these kinds of problems have an obvious brute force solution, and then they have a less obvious but optimal solution. And that less obvious solution is probably better than the brute force solution. So we're probably looking at our minimum runtime of linear. So let's think about how to achieve that. Well, okay, this is similar to a running maximum type of problem that you'll also find on LeetCode. A link in the description below. But what happens, you see, is if you run the simulation starting from a particular point in the loop, and you keep track of how much gas you have, you're going, you're filling up as much as you can at each particular stop. If you're running a net surplus, it'll work out. If you're running a net deficit, what you find is that you can actually discard all of the starting position candidates that you've seen previously, and you wind up being able to go through once. I'll cover that more when I go through the example. So when you're doing an interview like this, the structure I recommend is what we did. You talk about a few different options, and you talk about what the minimum runtime you can expect is. You talk about what the maximum runtime you can expect is, and then you shoot for as close to the minimum as you can get. In this case, our minimum is linear. That is our target runtime, and that's what we're going to build the solution around. And then you think about ways to achieve that, and as you're developing, you think about ways to avoid violating that. So what does a linear runtime look like? Well, typically that's going to be a for loop. So let's write a for loop. For what? What goes into this for loop? Well, we're probably going to be looping through these arrays are the same length, so we only need one variable, and then we can index into the same position of both of them. So int I equals, let's just start at 0. And then I is less than, I don't know, let's say gas.size. And then increment. So what happens is you declare a variable at the start of the loop. This check gets run after each, before each iteration of the loop. So, you declare this, then you do this, then you run this, and then at the end of each iteration, you do this. So this is before, this is after, and this is the start of the whole loop. So we have our index. And what this size variable returns, it does what it says. This is a method that exists on any container that's in the C++ standard library. And in this case, vector are containers. They're contiguous memory, and they're built for efficient sequential looping plus random access, plus you can add or remove to the length at the end. So you can't change the beginning, but you can add and remove elements from the end and in effect change the size. We don't need to do that here. Vectors are the original C++ arrays. They're not quite as raw as C arrays. And there are actual C++ containers called arrays, but those were added later. And generally, there's not a lot of reason to use those over vectors. Aside from maybe a software engineering point of view, they have more like guardrails on them, but from like what they can accomplish, they can't really accomplish things better or more efficiently than vectors can. So vectors are more commonly used. And size would return the number of elements in that container. So you could also say like int n equals gas.size, same difference. And since we're using zero-based indexing, we want to do our check that Ri is less than the size, because if it were equal to the size, you'd be indexing out of bounds when you go into one of these arrays. So I is less than n. What do we do here? we need something to keep track of our gas tank. So int gas equals, and it starts out at 0. That's dictated by the problem. All right, so let's go ahead and start running. So let's just say, let's just start running the simulation and see how it goes. So first, we want to fill up as much gas as we can. So gas plus equals, oh wait, I can't call it gas because that's clashing with the array. So let's call it tank. Tank plus equals the amount of gas available at this station for purchase. Gas I. And then let's see. If any point, okay. I'm going to add the check before, and I might change this as we go through this, but let's see if it needs to be done before or after. So if tank is less than 0, then what? What do we do? We need to do something. Actually, okay, that's fine. So we just arrived at our current position. If the tank is less than 0, the algorithm I'm going to go with, and that'll explain, particularly when we go through the example. So in these interviews, you run time, and then you code, and then you do an example. You want to mentally step through an example and execute it as if you didn't. Pretend you're working on a whiteboard. They want you to mentally run code and see your ability to make your brain be the computer, basically. That's what a lot of these interviews check for. Some of them, some companies are more liberal with letting you use a compiler or not, particularly if you're writing on a computer. But generally, they prefer to see you use that as little as possible. They want to see you run the program in your mind like a computer and have your knowledge of the syntax and stuff. It's just, that's your bread and butter. That's what they expect you to do all day, every day is code, code, code. So they want to make sure that you can do that as efficiently as possible, particularly in a, if you have like a really, 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 really complex, large program with lots of little parts and stuff, um, it becomes kind of unwieldy for IDEs, integrated development environments, to be able to give you like things like autocomplete or be able to check for syntax errors. Like sometimes they fail. So are you going to be able to operate in those kinds of situations where you're basically coding in a text editor? That happens more often than it should, I think, but often enough where they check for it and they want to hire people who can do well in that case. So if our tank is less than 0, we're going to discard all the previous positions. So tank equals 0. And then what? I'm going to keep track of the return position. So int return, ret for return equals, we're starting at 0, and then we're gonna so set our tank to 0, and we're gonna update this return position. Ret equals I plus 1, because we're discarding the current position as well. Okay, so we fill up so this is if we got to our position and we had a deficit of gas. Let's see. Do we want to discard the current position? No, let's keep it here for now. Let's not discard the current position yet. So if we arrive and we're less than 0, we discard all previous positions, we fill up, and we keep going. All right, so how do we know if we've succeeded or not? Well, it is theoretically possible for there to be no potential way to go around the entire loop. So suppose we're starting at the, we've gone through this loop, we've discarded everything, and we're at the very last position. So we're going to go from last to first. We either need to find some way to like loop back around and check, or we could just say, let's see. If we add the gas, let's see. I think if we add the gas afterward, but then we just keep track of a running total, then that would also cover it. So we have things like, so tank, and we also have int, let's see, total gas. And then we also have a total gas, consumed gas. This might be fine. So total gas consumed. So tank, add to the gas, total gas, add to the gas. Oh, we want to know how long the chip actually takes. So total gas versus int total total need, I guess. So gas, we add gas I, and then total need, we add the cost. Let's see, so these are costs to get to the next space. Total gas, total cost. We fill up and then keep going. And at the very end, if our total need is greater than the cost, I'm getting the names mixed up. I'm going to change this name because variable names are basically comments. So total cost, so total gas for gas, total cost for cost, total cost. Let's keep that. If our total cost is greater than our total gas, then there's no solution. So if so what this syntax means, this is basically if else. So you have this question mark. Before the question mark is a Boolean condition. So total cost greater than total gas. If this is true, then you do the first thing after the question mark, -1. And then if it's not true, you do the second thing, the thing that's after this colon here. So ret. So this value consolidates to -1 if this is true, or ret if this is not true. And then whatever this consolidates to would then gets passed to the return statement. So that's what that does. Let's see. Am I missing anything? I think this might be everything. I'm gonna go ahead and run the example to refine this, and then see if that works or if it needs some changes. I'm not seeing anything obvious right now, so I think it's close enough. First of all, okay, let me verify that this matches our linear runtime, first of all. So we're declaring these. Normally, if you want to check the size of something, it would be a linear time because you have to go through each element of that container and count up, how many are there. That would be linear, except in C++, containers usually keep a running track of their size. So this is already a variable that just exists. Gas just has this property. So this is a getter. This is not a calculator. So this would be constant time. It's just retrieving a single value. And these are all declaring variables. So these are constant time. And then this is a loop. We touch on each element of the array once. And then this is constant time. This is constant time. This is constant time. They're just adding a number. And when you're adding fixed size numbers, it's constant. Technically speaking, operations are linear on the number of bits. But when you have a constant number of bits, in this case, 32-bit integers, which is the default for C++, usually for most machines. But in either case, whatever machine you're using, it's a constant size. Then this linear thing collapses to constant time. So you have constant time here. And then Boolean check, that's constant. This is constant. Assignment, that's constant. So you have a whole bunch of constant operations inside of this linear time loop. So it means you have linear times constant, so you still just have linear. And then so you end up with constant plus linear. The linear dominates, so your runtime is linear. So that's how that works out. Now let me go through this example. I'm gonna do, I guess, this one. I like this example better because this first one, you have more gas at each particular station. So, well, no, because the expected output is in the middle somewhere because the costs vary. Okay, no, I'm doing this example. Okay. Okay, so there's our starting point. And then what are our variables? We have tank. That's 0. Return value. That's 0. We have total gas, which is also 0, and total cost. And then those are all our data structures. So let's go ahead and start. And then I'll write out, just for the sake of keeping track, I'll write out I as well. So we start out at 0, position 0. So we have n, okay, that's just the size. We initialize these, so we did that. Now we're in the loop. Tank, we're going to add the value of gas. So we're at tank, we're going to add 1. And total gas and total cost, we're going to also add 1. Or total cost, we're going to add 3. Oh, you know what? I messed up. So tank, we're going to add gas minus cost. Okay, yeah, this is necessary because, well, if we go to the next step, we fill up the current position, and then this cost has the cost to go from the current position to the next one. So we fill up here, and we subtract what it would take to get to the next one. So that's going to be what our tank has after leaving the current position and before filling up at the next. That's important. That's why we run these examples. All right, so tank is going to be, it's 1 minus 3. So that's actually going to be minus 2 there. Total gas, total cost, 1 and 3. Okay. And then what we have is, okay, so in this case, yeah, all right. So what we're seeing happening here is we finished this step. Now we're here, and we're checking if our tank is minus 0. Sorry, but less than 0. It is. It's minus 2. So what we want to do is, in this case, yeah, we do need to discard the current position. We cannot start at the current position. So we initialize our return value again to the next position over. And if that doesn't work out, then we'll bump it again. But right now we know that the current one does not work. Okay, next iteration of the loop. All right, we're at here, so 2 and 4. So I'm gonna put a star there so you can see. So we're looking at 2 and 4. So tank, we're gonna add the difference between the two, gas and cost. That is gonna be, you can see that's, we had set it to 0, but it's going back to -2 again because our cost is again 2 greater than the amount of gas available. And this we also would change as well. And then so this is gonna increment by 2, but this is gonna increment by 4. So 3, 4, 5, 6, 7. So you right now have total cost is the sum of these 3, and this sum of these is the cost 7. Okay. That's clearly not going to work. Our tank is below 0 again. What do? We zero that out. We bump our return value forward by 1. And then that's it. Next step of the loop. So sorry, I missed that. We're 0, 1, 2. We're here now. We're at index 2. So there. We're looking at these. All right. Okay. Let's keep going. Fill up our tank. Our tank is going to be +3 -5. That is again gonna get us -2 as our net value. Add the total gas, total cost. So 3, 4, 5, 6, 7 plus 5 is gonna get you 12. All right, this isn't gonna work either. Tank is negative again. So we're gonna reset that. We're gonna bump our return value forward to 3 total, and then that's it. Next step of the loop. This is where we expect things to be different because see this example here says our expected output is 3, and now we're index 3. So what's going to be different? Let's see what happens. Okay, in this case, we add 4 to our tank, and we subtract 1. So then it goes to 3. That's positive. Good. All right. And then total gas, total cost. So this goes to total gas plus 4 goes to 10. Total cost is 12 plus 1, that goes to 13. We have our gas availability rising faster than our cost. In which case, the tank value is not less than 0, so we can keep going. We don't hit any of this. And I guess for posterity, there's only one step of the loop left, so I'll do that actually. I was thinking about skipping it, but just to show. All right, index I is 0, 1, 2, 3, 4. Index 4, the last one. Tank, we're going to add 5 to it. So 3, 4, 5, 6, 7, 8. -2 brings us to 6. Let's see, it was 3. Yeah, okay. Difference between 5 and 2 is 6. So yeah, 6. That's our expected value. And then total gas and total cost, we're going to add 15 to our total gas, and we're going to add 2 to our total cost, which is 15. Really? Okay, so yeah, 15. Oh, it was, okay, it was low. Okay, so 15, and then 15. They're the same. We just eked out. So let's just, for sanity's sake, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 15. Total gas is 15. Total cost is 3, 7, 12, 13, 14, 15. Okay, total gas and total cost should be equal. That's fine. That's correct. And then we did that. We see that the end of our gas tank is not negative, so we don't run that. Our return value is still 3. That's our last iteration of the loop. We're done. So we hit this statement. Total cost versus total gas. Well, they're equal, 15 versus 15. So we do not hit, it's not a greater than situation. It's less than or equal to. So that is false, meaning we're going to return this return value. Okay, that's correct. Now I need to get into the details of why this works. Well, okay, so for any particular stretch, let's say we have suppose we were to start at 2 here. Suppose for a moment that we were to start at 2. Well, okay, we already ran this in our simulation. We saw that this ran -2. So like we discarded this first position and then we started there. So maybe it'd be more interesting if I say, what if we started at 4 instead of, well, what is this? Index 0, 1, 2, 3. No, this is the solution. So what if we started here instead? What if we started at this position, which is the less obvious case? Okay, in this case, our loop would look like here, 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 here. Here, 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 here. So we have this, okay, this 5 versus 2, good. I'm going to, just for the example, I'm going to write down what our net tank is. So here it's +3, that's good. So now we look at this position. We're back in that, in the situation that we did run step by step, we saw deficits. It is not possible to start at this first position. It's just not. So if we start at this other one that has a much more of a surplus, is that enough to carry us through? Hint, hint, the answer is not, but I'll try to illustrate that better. So we have a surplus of 3 after starting at this last position. Is that enough to carry us through? Well, we have a deficit here of, so 1 versus 3. That is a deficit of 2. So that brings our net surplus down to 1. And then here, 2 versus 4, that is another deficit of 2, which brings our, that overrides our surplus. So we had a surplus of 1, and then we ran a deficit of 2, and now our net surplus is gone. We're at a net deficit now. So this stretch of deficit ate our surplus. Can we do better? Well, we saw the, okay, this starting at 4, this is enough to carry us through this the surplus. And maybe I can run through that, but that was our solution. That was unique. The important thing to know is this unique criteria that the problem, it dictates. It says there's only one. Meaning there's only one starting position that is where your surplus, your temporary surplus is enough to carry you through temporary deficits later on. All the others are going to have a smaller surplus. So if you find one that works at all. All right, so for example, if you start at 4, so 4 versus 1, that's a surplus of 3. And then you add in that second surplus, so 5 versus 2, that is another surplus of 3. It gives you a net surplus of 6. And then you go through the deficit phase. So 1 versus 3, that's -2, so that brings you down to 4. 2 versus 4, that's another deficit of 2. And then 3 versus 5, that is another deficit of 2, but that's just barely enough. Is there a situation where, again, it says guaranteed to be unique. So it dictates there's only one starting position where the surplus you get early on is enough to carry you through all of the deficits that you go through. So you can assume when you're going through this loop the first time around, if you just start at index 0 like we did, always starting at index 0, if you go through a period of deficit and you don't hit some big bump, it's like realistically, it's what am I saying? We went through this initial deficit here, and we had maybe a net loss of 4. You're not starting at any position there, and by the time you get to 2, we started here, we discarded that. Well, why not try and run both of these? Well, suppose 2 gave us a surplus. If we're still, what am I saying? The starting position is always going to be in a surplus tile. So if you don't have a surplus, like it's just, what am I saying? It's always unique. Anyway, I'm going to wrap it up. This video has been long enough. And we have our runtime. We have our example. I'm gonna go ahead and write that down because I recommend you do that so that the interviewer does not have to remember, did we talk about this particular thing? They do want to know that you're looking at runtimes, that you're working towards a target runtime and not just kind of meandering through the code. So O of n time and O of 1 space. So what happens for space complexity here? This excludes the input and output. Well, actually, no, it just excludes the input. So like you can get away with reusing the input to have constant space. That's something to ask your interviewer about. Maybe they prefer you don't modify the input, in which case you have to make a copy, and then you end up with linear time, or sorry, linear space. Usually space complexity analysis is a little less interesting, but you should still mention it. What did we allocate? We allocated a fixed number of variables of fixed size each. Didn't allocate any sort of vectors or any like other kinds of containers that whose sizes depend on the size of the input. We just had a bunch of individual variables, so it doesn't matter how big the inputs get. We're going to have the same amount of space allocated inside this array. So it's constant space complexity and then linear time versus the input space. Linear time, constant space. I'm gonna give it a run for syntax. Cool, accepted, nice. And then submit. Boom. All right, gas station. Have a beautiful evening.